We rely on these incredibly complex systems every single day. Things like massive oil rigs, sophisticated spacecraft. When they're working, they are just modern marvels. But when they fail, the consequences can be absolutely catastrophic. Just think about the 2010 BP Deepwater Horizon disaster. That one failure, just one, had an estimated financial cost of $10 billion. I mean, that's a number that's almost impossible to wrap your head around. But as staggering as that number is, it's not the one that really matters. This one is 11. 11 people lost their lives. And that just highlights the immense human responsibility that comes with managing these systems. It's never just about the money. It's always about people. So this gets us to the core questions of this whole explainer, right? How do these catastrophic failures even happen? And way more importantly, what can we possibly do to stop them? Well, it turns out the answer lies in completely changing the way we think about failure itself. See, if we want to prevent these failures, we first have to really understand them. And it turns out there are two fundamentally different kinds of failure. And treating them the same, that is a very costly mistake. On the surface, these two words look almost identical: systematic and systemic. But understanding the difference between them is the absolute key to managing complexity. One is about a single broken part. The other, it's about an entire system of interactions that has gone wrong. Okay, let's start with systematic failure. This one's pretty straightforward. Think about a faulty brake pad in a car. It fails predictably because, hey, there's a specific flaw from the factory. You can trace the cause, find that one broken part, replace it, and boom, problem solved. It's a nice, clean cause and effect relationship. But systemic failure, whoa, that is a completely different beast. This is the kind of failure where every single component could be working perfectly exactly as it was designed. The failure doesn't come from a faulty part. It comes from the complex, unpredictable interactions between the parts. The system as a whole creates an outcome nobody saw coming. As the saying goes, the whole truly is more than the sum of its parts. So, if the problem isn't one broken component, but it's at the system level, how on earth do you fix it? You can't just swap something out. No, you need a whole discipline that's designed from the ground up to engineer the entire system. And that discipline, my friends, is systems engineering. Now, this isn't about being an expert in just one little area. It's a holistic approach, a way of thinking that manages a system from the first sketch on a napkin all the way to its retirement. Its job is to bring all the different teams, mechanical, electrical, software, you name it, into one structured, coherent process. One of the core frameworks for making this happen is called the V model. It might look simple, but don't let that fool you. It's an incredibly powerful map for designing, building, and testing a complex system to make sure you actually get what you wanted at the end of the day. The left side of the V is all about breaking the problem down. You go from the big picture down to the tiniest details. You start with what the user, the stakeholder, actually needs. Then you turn that into specific technical requirements. Then you create the blueprint, the architecture. It's like going from the fuzzy idea of a house all the way down to the design for each individual screw. Then you move to the right side, and it's all about building it back up, piece by piece. As you put the components together, you test at every single step. First, you verify. Did we build this thing according to our own blueprint? Then, at the very top, you validate. Does the finished house actually meet the homeowner's original needs? The V model is what keeps you honest and ensures what you built is what you meant to build. Okay, so the V model gives us a roadmap. That's great. But what are some of the actual practical tools that systems engineers use to manage risk and prevent those devastating systemic failures we've been talking about? Well, one really powerful tool is called Layers of Protection Analysis, or LOPA. The best way to think of this is like a series of safety nets. The first and most important layer is just designing something to be inherently safe, making it really hard to fail in the first place. If a problem gets past that, basic controls try to fix it. If that doesn't work, critical alarms go off to alert people. And only as a last resort does an automated safety system kick in. Each layer is another chance to stop a disaster. So why go to all this trouble? I mean, this all sounds like a lot of work, right? Well, it really comes down to a simple, powerful calculation. There's what we call the cost of conformance. That's the money you invest upfront in prevention. But that cost is tiny, absolutely tiny, compared to the cost of non-conformance, which is the price you pay for failure. The takeaway here is crystal clear. It is always cheaper to prevent a disaster than to clean one up. Another fantastic visual tool is the bow tie model. It is just brilliant for visualizing risk. The knot right in the middle, that's your potential disaster. Over on the left, you've got all the threats that could cause it and the barriers you put in place to stop them. On the right, you have the awful consequences and the recovery barriers you have to minimize the damage. Suddenly, your entire risk landscape is on a single, easy-to-understand page. Now, these models have been the bedrock of safety for decades. But today, technology is giving us even more powerful ways to apply these ideas, tools that honestly feel like they're straight out of science fiction, like the digital twin. And this evolution is all happening in what we call the age of Industry 4.0. This timeline really puts our current moment in perspective. I mean, first we had mechanization with steam power. Then we got mass production thanks to electricity. Then came automation with computers. And each leap forward made our systems more complex. Today, we're in the fourth industrial revolution, and it's powered by something called cyber-physical systems. So what are cyber-physical systems? It's basically where the physical world of machines and the digital world of software and data they merge. The factory floor is now connected to the internet. The machines, the sensors, the software, they're all talking to each other in real time. This creates a whole new level of systemic complexity, but it also gives us incredible new opportunities to manage it. And this leads us to what might just be the ultimate tool for a systems engineer, the digital twin. I want you to imagine a perfect virtual replica of a jet engine, or a wind turbine, or an entire factory. And this isn't just some static 3D model. It's a living, breathing digital copy, constantly fed with real-time data from its physical counterpart. With a digital twin, you can run simulations, test crazy failure scenarios, and optimize performance, all without ever putting the real-world asset at risk. It's a game changer. Which brings us right back where we started. The systems theorist Russell Ackoff really said it best. Complex problems do not have simple solutions. When something goes wrong in a complex system, searching for that one single broken part is usually looking in the wrong place. The real challenge and the real solution is in understanding the interactions and engineering the whole system. The essential question isn't which part broke, it's how did the system's interactions allow this to happen?